In a typical light scattering scenario, light can interact with molecules and they will just being scattered away. There's no exchange in energy or momentum. And that is called Rayleigh scattering. So that is the predominant process. If you shine, let's say, 1,000,000 photons to a molecule, chances are all of them except one or two are being scattered in Rayleigh scattering process. Sometimes you will encounter a low probability event. There are two kinds of low probability events. In one case, photon come in, and your molecule is in a vibrational ground state. And the molecule would undergo vibrational state excitation, taking energy from the incoming photon, and emit a new photon that has lower energy compared to the incoming laser. Remember, the incoming photon is monochromatic because it's a laser. So this is the kind of signal that produces the Raman signal. As I said, there are two different kind of low probability events. The other one is the molecule is in excited vibrational state. Now the laser coming in, the photon actually de-excite the vibrational state, and as a result, emit a new photon that is higher in energy. Okay. So both kind of process can produce Raman signal, but the first one is more common. Why is it more common? Because at room temperature, most of molecules are in their vibrational ground state. So you are more likely to encounter a molecule in vibrational ground state than having a molecule in a vibrational excited state. And actually, if you look at these two kinds of Raman signals, they are called Stokes and anti-Stokes. By looking at the ratio, you can figure out the population ratio of molecules in ground state vibrational energy level and excited state vibrational energy level. You have taken PCAM, you will quickly recognize that should be based on Boltzmann distribution. And if you know Boltzmann distribution, there's a parameter called temperature. So Raman spectroscopy can actually give you a temperature of a molecule by looking at the vibrational distribution, energy distribution of a molecule, by simply looking at the Stokes and anti-Stokes lines of the same Raman signal. All right, so this is a very useful technique for 2D materials, in part because if you are using a laser, you can focus the laser using a microscope into a small area, limited by diffraction. So if you are using a visible laser, let's say 514 nanometers is a typical laser wavelength people use. That's the grain laser pointer type of wavelength. You can focus that kind of laser to a point less than half micrometer in size. And you can get signal from that small area. And that is why people sometimes use micro-Raman in their analysis. And you can do this in a point-by-point fashion. So you can create a Raman image, getting a map of 2D material, each point representing one Raman spectrum. And you can get information about the heterogeneity of the sample using this technique. That's the Raman mapping. All right, so this is a very useful technique, but as I said, Raman spectroscopy usually is a low probability event, once in a million. Okay. Having said that, a lot of 2D materials are actually being characterized by Raman spectroscopy in a very satisfactory way. Two reasons. For one, a lot of 2D materials, they are semiconductors. They have band gap absorption at the laser wavelengths. And when that happens, there's a process called resonance Raman enhancement that can greatly enhance Raman cross-section by millions of times sometimes. There's another trick that people also often use. That is the substrate. is something I didn't mention in my talk in the morning, but a lot of the substrates people use to support 2D material is silicon wafer with an oxide, with a silicon oxide top coating. Now that coating can sometimes become an optical cavity. Imagine you have a flat silicon surface, that is a mirror, and you have an oxide coating that is several hundred nanometers in thickness, and the refractive index of silicon oxide is about 2 something. So if you think about this combination, it actually approaches the wavelengths of visible light in many cases. So light can come in and come into the silicon oxide layer, being reflected by the silicon layer, and undergo multiple reflection. And if the thickness of the oxide is correct, is the right one, it can either enhance the reflection or reduce the reflection. You could have a scenario where light being trapped within the silicon oxide layer, and whatever material being deposited on top of silicon oxide undergo multiple excitation, and that can significantly enhance the emission, the Raman emission, and also effectively subject the material to higher optical excitation than you would have calculated using merely the light intensity of the laser, of the incoming laser. So, having said that, I want to show this optical photograph. This again, let's see this. So, photograph in the middle is an optical photograph. You see this is the purplish color. This is a signature color you would get from a silicon wafer with about 285 nanometer of oxide thickness. How do I know that number so precisely? Because that number is pretty important. If you make it too thick or if you make it too narrow, too thin, you will not be able to see graphene deposit on those surfaces, because the optical effect, the interference effect I mentioned would cancel the contrast in some cases, in some thickness, and enhance the contrast in others. And in the case of graphene research, people often use oxide thickness around 280 nanometer also, and that turns out to be a thickness that can enhance the optical contrast of graphene, and by the same reason, enhance the Raman response of graphene. So for graphene samples deposited on those samples, those kind of substrate, you can produce a pretty strong Raman signal by using Raman laser intensity as low as a milliwatt or so. You can get very decent Raman signal by integrating a couple minutes using the milliwatt of signal, focus onto a diffraction limited spot. That is actually a very strong Raman response, knowing that you only have one layer amount of material. Now, if you can deposit a graphene onto another substrate, you may not be so lucky. For example, the graphene sample on copper, supported on copper substrate. In that case, you don't have this optical cavity. In those cases, you have to integrate your signal for like an hour before you get any meaningful signal. And oftentimes, an hour is not enough. So the Raman signal is particularly useful in carbon research, and hopefully I'll have more time to talk about this tomorrow, but sufficient to say there are 3 important Raman peaks from carbon. They are all very sensitive to the structure of graphene. You look at the spectra on the right-hand side, and this is 4 different spectra of graphene separated by the actual layer thickness. And on the 1 layer graphene, you see 2 permanent peaks. There's one around the 1580 with numbers. That is so-called G peak. You have to think about the actual molecular vibration. You can think at the stretching of the carbon-carbon double bond, something like that. Now, the vibration in the bulk graphene is different from molecular species because there are different symmetry selection rule being imposed. Now, this peak would be proportional to the number of layers. If you look at the vertical stack, you find the more layers there is, the stronger the G peak there is. That's pretty much linear. If you double the layer thickness, you double the intensity there. There is also a very strong signal around 2700 wave numbers. This peak, oftentimes is called 2D peak. Some other people call it G prime peak. People use different names. Some have very strong feelings about what the name should be called. But 2D and G prime are probably the most often used names in the literature. One way to think about this peak is this can be viewed as an overtone of the so-called D peak, which I'll mention in a sec. This one is very sensitive to thickness as well, but it doesn't really change the intensity as a function of thickness, but rather it changes the shape. So for monolayer graphene, it shows a very simple single Lorentzian line shape. But for two-layer and thicker layers, there are actually more components. In the two-layer case, I think there are at least 3 or maybe 4 components of different peak components. In that peak, you see this obvious line broadening. In addition, it's also sensitive to doping. Depending on whether the graphene is doped with extra electron or extra hole, it will shift to different direction. Now, on the left-hand side, I also show additional data taken from the liquid exfoliated graphene. And if you compare these two, you'll find there's this one additional peak around 1350 with numbers. And this one's so-called D peak, or you can think about it as defect peak. This one comes from essentially defects. If you have to think about molecular vibration picture, that would be the ring breathing mode. If you think of benzene, there's a ring breathing mode. You know, the ring becomes bigger, smaller, and that vibration has energy around 1350 wave numbers in bulk graphene and graphite. Now, if you think about the bulk, as I said, they're different from molecular species. Because in the benzene ring, in a molecular benzene ring, you have this ring breathing mode. But in a bulk graphene, you cannot have that breathing mode if there's no defect, because you cannot have all the rings breathe at the same time. It just doesn't work that way, because it's infinite chain of rings. So this mode would only be possible if you have defect embedded in the lattice, so that will activate, that will break the symmetry and make the ring breathing mode a possibility. So having this peak showing up would be an indication of structural defects in graphene structure. That can be an edge, can be a point defect, can be a 5-member ring instead of 6-member ring, so on and so forth. The intensity of the D to G peak, the ratio of these two, is often used as an indication of how much defect there is. And there are all kinds of calibrations you can find in literature. I don't want to go to the details, but you can essentially link the D to G ratio to some kind of defect density. Again, people have very different ideas how this kind of correlation should be made. But even given this complexity, there's a very good calibration you can follow. Okay. So the last thing I forgot to mention is there's also the effect of strength, mechanical strength. Because this is a single layer, atomic layer material, a lot of 2D materials are actually very flexible. You can stretch them, you can compress them, just like a plastic membrane, a rubber membrane. Yeah. In the case of graphene, you can actually stretch the graphene to a very significant degree. People have shown that single layer graphene can be stretched 10% or something like this. this. This is unimaginable in any other bulk material. Single crystal metal, for example, can be pulled about 0.5% and then it will break. So this is an incredible material in that kind of context. The mechanical strength will also show up on the GM2D peak. You'll see a progressive shift of those peaks depending on the strength being compressive or the other way around. All right, so that is Raman, and as I said, Raman has been used in all kinds of 2D materials research, not only limited to graphene, but also TM. A lot of TMDs have been characterized by graphene. Again, there's similar behavior there, although not exactly the same. But the sensitivity of the Raman signature with respect to number of layers, and doping level, and the strength has been a common feature in 2D materials research. Now to switch gear a little bit to XPS and UPS. Those are two techniques are commonly used in surface analysis. XPS is X-ray photoelectron spectroscopy, and UPS is ultraviolet photoelectron spectroscopy. They are very similar technique in that they follow the same kind of concept. So in both cases, you shine a photon into atom. In the XPS case, it's X-ray photon. In the UPS case, it's also a DPUV photon. Same principle, except the energy is different. And the photons would interact with the electrons in the atom, and it will essentially kick off one of those electrons. Now, depending on the energy of the photon, the likelihood of which electron to be kicked out would differ. Sometimes it's a deep S-level electron. Some other cases it's more valence shell electron. Because the cross-section of electron-photon interaction depends on the photon energy. And as a result, there will be a different selection or sensitivity or preference of whether exciting a core-level electron or valence shell level electron. Now, regardless of what electron is being kicked out, it's being kicked out. And what you can do is you can collect this photoelectron, and from there you can measure the energy of this photoelectron. And from there you can figure out which kind of atom this electron is coming from. So with XPS and UPS, you will have this ability to get some atomic elemental composition information. And even more precisely, the oxidational state of the element would impact the exact energy of the photoelectron, sometimes called binding energy. And typically a higher oxidation state, so more positive charge, would produce a higher binding energy of the photoelectron. So this tiny shift, usually just a couple of eV, or less than the eV, will give you a little bit of more chemical information, even though it's not a lot of chemical information about the oxidation state of those elements. So the benefit of both XPS and UPS is high surface sensitivity, and the reason being the photoelectron does not travel very far in solid materials. They got captured, they got scattered. So the X-ray actually can travel very deep into material. A lot of materials, X-ray can travel micrometers, even millimeters deep, not a problem. But the photoelectrons, even though they are being generated everywhere in the material, only the photoelectron generated on the top surface can escape the material. The mean free path of a lot of photoelectron in solid state material within the context of XPS is a couple of nanometer, maybe tens of nanometers in some cases if you're lucky. So in other words, only the top few nanometer of material can generate photoelectron, and those photoelectrons can escape. Okay. Additionally, because because the mean free path of the electron is so short, the most likely survival pathway of the full electron of getting out of the solid material is going vertically up. If it goes in an angle, so if I have my material to be analyzed, and I have full electron generated here, if it go up vertically, it will go through the least path possible. Okay. But if you go vertically, it will more likely to be absorbed by the material without being escaped. So what that means is if I have my detector, if I can change the angle of the detector relative to the normal of the surface, I'll get different information. Why? Because imagine I have 2 points of photo emission, one near the surface, one deep in the surface. If my detector is closer to the surface, then most of the signal will be the one coming from the surface. Whatever deeper signal will be absorbed, their photo electron is not going to escape. However, if I increase my detection angle to the normal, I have more likelihood to see the photo emission deeper in the sample. So by changing this angle, I can change the surface sensitivity with lower detection angle, giving me more surface sensitivity, with detection angle near 90 degrees, giving me least surface sensitivity. But even at the least surface sensitivity configuration, I still get most signal coming from the top few nanometers of the surface. Now, if I do this kind of angle resolved measurement, and I put my data into some kind of mathematical model, I can figure out exactly where my signal is coming from. You can figure out which signal is coming from the surface, which one is coming from deeper the surface. And that sometimes becomes handy when you have, for example, 2 layers of 2D material stacked on top of each other, and you want to show, oh, I have molybdenum disulfide on top, and I have graphene on bottom, or vice versa. XPS can tell you that by doing angle resolved measurement. On the right-hand side, I show typical XPS data on the top, and also UPS data on the bottom. Let's see if I can move this. So the UPS data in particular is interesting in that it shows a lot more chemical information that you do not see. Somehow this is, okay, I'll give up. But you probably see that the UPS, even though only part of it is visible, there's a lot more change. You see there's a lot of growth. So what I show here are graphite samples exposed to air for different amount of time. Now you see in this graphite sample, which is different from graphene and copper again, okay? The XPS data actually doesn't show any difference. You know, after exposing the you see the XPS part doesn't show any difference after I leave the graphite sample in air for 20 hours. But the XPS data showed dramatic difference. And that's in part because, as I said, the XPS and UPS are sensitive to different parts of the electron. In the case of XPS, it's sensitive to the 1s shell, and in the case of UPS, it's the 2p shell and the valence shell. And the sensitivity is very different, and that showed up in this dramatic evolution that you can observe in UPS, showing that there's actually a lot of organic materials deposited down on the graphite, but not showing up in the XPS. And last part, I want to talk about atomic force microscopy. Again, this is a highly versatile technique. How this works, you have essentially a needle. Think of my finger as a needle, and this needle vibrates because there's a piezo driver vibrates this needle, and vibrates at very high frequency, about typically a couple hundreds hertz. The experiment we do in our lab typically use the tip that vibrates at about 300 kilohertz. Okay, so 300,000 times vibration per second. Now this needle would tap the surface, and there's a piezo driver to detect, to move the sample, and there's also a laser. You see, so that's the needle I'm talking about, and there's a laser shooting onto the back of the needle, and being reflected. The light is essentially a cantilever. You can magnify the movement difference, and there's a detector here. It detects the movement of the laser beam as a result of the vibration. So this detector can know how much vibration there is and what is the magnitude of the vibration. It can actually also detect many other things like the phase and so many different things. But sufficient to say that the detector will be able to tell whether the tapping has been in contact with the surface or not. Because once the tapping is in contact with the surface, the magnitude of the vibration is smaller. And what the system can do is it can create an internal closed loop system to automatically lower the surface or raise the surface so that it will maintain certain constant contact between the needle tapping and the substrate. And also can scan the substrate X and Y direction, and also remember there's a Z direction closed loop. So by doing this consecutive scan, you can create a topography image of the surface. So that's the so-called tapping mode. You can also do it in a different way. You can decide, I'm not going to do any vibration. I'm just going to use it as a needle. I'm just going to touch the surface and get a feeling of what kind of stuff on the surface. That's an oversimplified way. But if you do it that way, you can also get an image that's called contact mode. You have more interaction with the substrate, but you get more forceful intrusion of the surface. If you have a liquid layer or you have something viscous that may be masking the contact mode imaging. What's more interesting, certainly this will give you a lot of topography information that 2D material research is very much care about. But it's also a versatile technique in terms of getting additional material properties. There's so much you can do by adding another component of interaction to the tip, between the tip and the substrate. And there I list 3 different expanded AFM techniques, so to speak. One is the conductive AFM. I'm going to show one example tomorrow. And this is the case where you just add a voltage between the tip and the substrate. And certainly that would assume your tip is conductive and your substrate is also conductive. And in this case, you can measure the current passing through the tip to the sample. And you can get a local conductivity data from this kind of measurement. In the middle is so-called electrostatic FM. This is a more complicated case. Here you do two different kind of measurements. First, you do a topography measurement, so you get a sense of what kind of surface topology it is. And once you do that measurement, then you come back and image the surface again, but do it slightly differently. You're going to lift your sample a little bit up, about 10 to 100 nanometer up, typically several tens of nanometer up. You're going to apply a little bit of potential to the between the tip and the sample, and you're going to look at the vibration phase lag of the tip. And this phase lag will change based on electrostatic interaction experienced between the tip and the substrate. So this technique will allow you to detect the presence of charge on the surface, down to single charge or even partial charge on the surface. So you have molecules, you have for example, nanoparticle that is being fully excited and produce a charge separation. This technique can tell you how many charges are being produced on your nanoparticle, how many are being injected into your substrate. The last one is a very similar technique called Kelvin probe force AFM, and this is very similar to electrostatic AFM, but using a slightly different methodology to detect the surface potential, not charge separation, but looking at, for example, oriented dipole on the surface. If you have organic molecules oriented in a certain way, this can produce a surface dipole, and that can be detected by, that will produce a change of surface potential, which will be detected by the Kelvin probe force microscopy. Similarly, if you're working with 2D material, a major component of a lot of electrochemical study and also nanoscale electronics fabrication involves doping of the material. The doping would change the surface potential as well, and that, again, would be detected by Kelvin probe microscopy. So the kind of expansion is almost limitless. You can do mechanical measurements, you can figure out the mechanical response, you can figure out the magnetic response from material, so many different things from one very simple technique that is just tapping of surface using a needle. So I'll stop here and I know Professor Ken is going to talk about other practical things that might be relevant. So I'd be happy to entertain any questions at this stage. Again, this is a very interactive format, and I'm trying to share some of the practical aspects of research in 2D materials in this setting. And if you have any, practical questions or tricks you want to know in research in this area, I'd be happy to discuss this as well.
So you may ask questions relating to these characterization techniques that Professor Tao has just covered. The AFM technique, atomic force microscopy, the Raman, as well as one more technique that you have just covered. So XPS and UPS, of course, the ultraviolet photoelectron spectroscopy and X-ray photoelectron spectroscopy. If you have any question relating to that, I once again request you to please get yourself involved. Listening is good, but asking is very important. Ask questions. If you have any query, please ask. In case you have a query relating to today's topic, even tomorrow, you can also ask the next day. Now I'll be speaking on electrochemical techniques which are used for the electrochemical characterization of a system, mainly used for sensors, also for energy storage devices, fuel cell. So for these three types of systems, we use these techniques, the LSV and CV, linear sweep voltammetry and cyclic voltammetric techniques. Just a second, I'll be starting. Thank you, Professor Tao, for back-to-back 3 lectures, full of energy. Still, you are looking very energetic, full of lots of learning, and we have learned a lot. The students learned a lot, and definitely there will be some deliberations also. Maybe during the tea session or tomorrow also, we'll be having some discussions as well. Thank you. Chairman sir wants to say something. The electrode system is very useful for detailed analysis of the electrochemical behavior of a particular electrode. Clear? The information which we are not able to get from a 2 electrode system, or the information is not much reliable, that can be obtained with the help of a 3 electrode system. Before actually taking dive into how the reaction, how the system is being connected and how the data is being generated, there is a basic question: what is the difference between a chemical reaction and an electrochemical reaction? A chemical reaction involves breaking and formation of bonds. Some old bonds have been broken, new bonds have been formed to give a new compound, resulting into a new compound. On the other hand, in case of an electrochemical reaction, the electrons are transferred through an electrochemical or through an external circuit. There is no direct transfer of electron. Electrons are transferred through an external circuit, resulting into the oxidation of one component by the reduction of the other component. Similarly, it is written chemical and electrochemical reduction. Since a chemical reduction is basically a reduction by the chemical species, one species is reducing the other. While in case of electrochemical reduction, reduction means the electron are taken up by the component. So electrons are being accepted from electrode to the component, and that component is reduced. Similarly, in case of oxidation, the electrons are transferred to the electrode in case of electrochemical oxidation. For a normal chemical oxidation, the electrons are transferred to some other species which undergo reduction. Now the two, I think we have focused mostly on cyclic voltammograms here, but this, as I said, LSV is also very important technique. Linear sweep voltammetry, as I said, in the case of voltammetry, we sweep the potential, we vary the potential, we give different potentials to the system, and in response to that potential, the current which is being generated by the system is first of all calculated and then it is plotted. In case of LSV, we vary the potential in one direction only. For example, if we are starting from -1, we are taking it to +1 only, or from 0.5 to 1 volts. But we are not taking it back because it is only a linear process, it is not a cyclic process. So in case of LSV, we vary the potential in one direction only. While in case of CV, since the word cyclic is there, we vary the potential in two directions. First of all, we take the potential from -1 to +1, then again from +1 to -1. And that is why we call it as a cyclic system, and duck-shaped curves are obtained as a result of this cyclic voltammetry, in which current is being monitored against the input potential, and that potential is varied in a cyclic fashion. As it is written, a cyclic voltammogram plots current y-axis and potential x-axis. The potential is swept linearly with time between the defined limits. For example, as I said, from -1 to +1 and then from +1 again to -1. So that it is very useful for reversible reaction, because in a reversible reaction we have one component, for example, is oxidizing to give a reduced oxidized product, then again that oxidized product is accepting electrons, showing the reduction reaction. So it is a cyclic process. So for reversible reaction, cyclic voltammetry is the most preferred technique. And nowadays, I have seen most of the people are working on this technique, because whether it is the sensing technology, electrochemical sensor, or the energy storage devices, all the electric vehicles which are being developed, the lithium-ion batteries which are being used, They all are basically characterized by these techniques. Even the phone battery which you are using in your phone, they are being characterized by cyclic voltammetry technique. And the batteries are also characterized by GCD, which is also known as galvanostatic charge discharge, to check how a battery can store charge and up to how long a charge can be stored in a battery. So the electrochemical setup it basically consists of a working electrode. Working electrode is the main electrode at which the analyte is undergoing oxidation or reduction. It is the main electrode at which the analyte is responding. Carries out the electrochemical reaction of interest. The common materials which are used as a reference electrode, I am sure you must have studied the electrochemistry in your BSc or in MSc, and there you have studied various types of reference electrodes. Although we have standard hydrogen electrodes that can also be used, but storing and transportation of standard hydrogen electrode is a bit difficult, because standard hydrogen electrode, I think you still remember that there is a platinum wire dipped in a solution of 1 molar HCl concentration, and hydrogen gas is continuously pumped into it at 1 atmospheric pressure. So storing that electrode needs continuous supply of hydrogen gas. Transportation becomes difficult. Therefore, instead of standard hydrogen electrodes or other electrodes, we prefer either the glassy carbon electrode. We may also have a silver chloride electrode, which is one of the most commonly used reference electrode. You can also use calomel electrode. These two electrodes are the most commonly used electrode. The silver chloride electrode, which comes under the category of metal insoluble salt electrode. पढ़ा होगा आपने, metal insoluble salt electrodes. So they comes under that category, calomel electrode or the silver chloride electrode. They are mainly used. You may also use glassy carbon electrodes. They are basically that I am telling of reference electrode. Okay. So in case of working electrode, I said you may use a glassy carbon electrode, or you may also use carbon paper available in your lab. If you are working on a material, just take that material, deposit a coating on that support. That support may be a glassy carbon electrode or a platinum electrode. Most of the time we do not use platinum electrode because it is very costly. So we prefer other electrodes like glassy carbon or carbon paper or carbon felt. Then the second electrode, which is called as the counter electrode. Counter electrode is basically used, platinum wire is used as a counter electrode. It completes the external circuit. Typically has larger surface area than working electrode. It is used in the form of either a platinum wire or a platinum disc. Then comes the reference electrode, the examples of which I have already given. You may also use a standard hydrogen electrode, but we prefer, because storing and transportation is easier, we always prefer silver chloride electrode or calomel electrode. We are using in our lab silver chloride electrode as the reference electrode. Now preparing for experiments. Before taking the LSV or CV experiments, we always starts with a good solvent, because these experiments are carried out in a liquid media. That media could be water, that could also be an acid or an electrolyte or a basic electrolyte. That you have to select. Or if you are not aware that your material will work very good in acid or basic media, then what you can do is just perform a simple LSV measurement in acidic condition, basic condition, and where you get the best answer, you may start with detailed experiment in that particular solution, whether it is acid system or a basic electrolyte system. Then supporting electrolytes, typically because it's an electrochemical system, the solution must have good conductivity, so we use electrolytes to improve the conductivity. So a typical salt that increases solution conductivity and limits analyte migration is used. We sometimes use KCl also. We may also use tetrabutyl ammonium salts or maybe some other salts depending upon the availability. Then comes the electrode preparation part. We'll also show the video tomorrow for electrode preparation, and for CV measurement we'll show the video today. Electrode preparation, before preparing the electrode, for example, if you are working on a glassy carbon electrode, you must have to clean the glassy carbon electrode with the help of ethanol or some other solvent. Once the electrodes are clean, then only you may go for coating of your material on the electrode. The material which you have prepared, you have to coat it on the electrode, and before doing the coating, you have to clean the electrode. Otherwise, your coating will not be uniform and your coating will not be stable. Once you complete the coating, if you have not cleaned the electrode, you put the electrode inside the system, your material will start basically wearing off. It is start getting into the solution from the electrode. So you have to put a stable coating, a uniform coating for correct results. Then data collection, the best practices for data collection include so the best practices for data collection. First of all, prepare your electrolyte by dissolving a suitable electrolyte in water, maybe 2.2 molar or 0.25 molar. But the most important thing before carrying out the experiment is to completely remove oxygen from the system, because oxygen is a good electron acceptor. If you have not removed oxygen, it will take up the electrons, while the analyte, because of that, may not show the required oxidizing or reducing activity. So for good results, you have to completely remove the oxygen from the system, and for that we bubble the system with any inert gas. Most of the time we prefer nitrogen, readily available, the cost is also low. You may also use argon or helium, but we prefer nitrogen gas. We pass nitrogen gas into the system, we bubble it for 5 to 10 minutes so that all the air has been removed from the systems and the system is completely under anaerobic conditions. Then we take the system for a study to ensure that there are no oxygen or there are no other electron acceptor except the analyte, so that analyte may give the response. If any other electron acceptor will be there, instead of analyte, the oxidation or reduction of that electronic acceptor will take place and you will get no useful information will be obtained. Then running the experiment, add the analyte, record the voltammograms and at least take 2 or 3 readings, and also check the reproducibility of the electrode preparation. It may happen that you, for the first time, if you are doing, you have got good result, but you always have to check the reproducibility. It may happen that you have incurred some error. So if you have incurred some error for the first time, the error will not be the same during the second or third measurement. Therefore, always do your experiment, reproduce your experiment 2 to 3 times. Record some background data also. Take a background scan so as to know if some impurities are present or not. If there are certain impurities, there must be some peak during the background record as well. However, if the background record is clear, there will be no such impurities, there will be no such peaks in the system, and then you may safely add the analyte and start your experiment. As I said, minimizing because for good data practices also I have explained, same is the concept for minimizing experimental errors. Clean your electrodes, maintain inert atmosphere, remove oxygen by passing inert gas, reduce ohmic drop. Ohmic drop is basically defined as the resistance which is created by very high concentration of electrolyte. So you do not have to take very high concentration of electrolytes. You have to keep the concentration of electrolytes low. You have to keep the solutions dilute for proper data analysis.
Sorry to interrupt you, sir, but slides are not moving. I'm not able to follow your presentation.
Voltammograms are used for studying the complex mechanism. Even LSV fails to give information about the complex mechanism. There we use cyclic voltammetry. It is also used for diagnostic criteria and various other chemical as well as electrochemical reactions. It is used in the sector of renewable energy for the characterization and testing of fuel cells. It is also used for, as I said, for sensing, electrochemical sensing. I am sure you all must be aware that the glucose sensor used for sugar monitoring is also an electrochemical sensor. And the sensor basically consists of 2 main components, the sensing element and the transducer. The sensing element is the electrode which we use to put the blood drop, and the transducer basically convert that oxidizing or reducing data into an electrical signal which we read with the help of that machine. So the sensor is not that machine, it is that electrode which is available in the market on the medical shop. So this is the difference in LSV. The potential of working electrode, as I said, is swept linearly with time in one direction only. While in case of say CV, the potential is varied in both the directions in a cyclic fashion, forward scan and reverse scan. The resulting plot is called as linear sweep voltammogram. The current is, while in the other case it is called as cyclic voltammograms, a duck-shaped curve is obtained. We have peak current values for oxidation as well as reduction cycle because it is used for reversible reactions. And LSV is primarily used to study the onset potential of redox reactions and provide information about oxidation and reduction potentials. It is not preferred for reversible or quasi-reversible. Quasi-reversible are just like pseudo-reversible reactions. Even for those reactions it is not used. Now I am going to show you a video where you can see how these data, how the electrodes are connected to the terminal, how we operate the system with the help of software to calculate the data.
video we have shown the demonstration of our potentiostat, and after that we have also synthesized the material, already synthesized material, and then prepared electrodes. And so on, you have seen the image that this is the silver electrode and the electrolyte, silver chloride electrode, and the analyte here. After that, we will show you in this video how to fabricate the electrode. We have used the classic carbon electrode. First of all, to prepare the electrode, we have to make a cell
after some impurity which immediately reacted with the iron plus 3 to form a different compound. Instead, if that impurity was not present, iron may have reduced back to Fe plus 2 form. If that impurity was not there, the system may work as a perfect redox system, but since some impurity was there, it immediately trapped the Fe plus 3 ions, resulting into some other product. Then the curve will not be exactly a duck-shaped curve. There may be some situations like that.
This voltagram is of graphitic carbon nitride, which is a 2D material, and we have performed this in 1 molar QS solution. So we are not getting the oxidation peak, but we are getting the reduction peak. So now we are exporting the data.
And you will notify. Doing it for LSV. The connection remains same. Everything remains same because LSV and CV both work on 3 electrode system. So there has been no change in the connection. The terminal has already been connected. While taking CV, it will remain as such. We just change the software. This time it will only be linear.
Now we are entering the scan rate.
यहाँ पर हम लोग we have to enter the scan rate, the potential window from 0 to 1 or from -1 to +1 and the scan rate.
Current range, there are some settings which depend on the software. Now we have taken the current range from 10. It's very fast. So this is the LSV. This is the first time demonstration. We will show you the detailed demonstration on the 3rd day of the program, in which we have included the galvanostatic charge discharge and electrochemical impedance spectroscopy also. So we will show the how to perform the supercapacitor, how to evaluate the electric supercapacitic performance of the electrode material. So we will show everything on that day. So this is the first time demonstration because of the time. So we have fast. So this is the linear sheet voltammeter, which is going in one direction only. Now it's time. So we will show you this video again after completion. The voltammeter is now voltage for this. So we will export the. On the 3rd day we will show you the potentiostat here and also give you the detailed explanation about the software, how to use it, and how to perform cyclic voltammeter and GCD and EIS. And how to evaluate the electrochemical properties of any electrode for supercapacitor. And we will show you some of our recorded voltammeter of cyclic voltammeter and EIS on the 3rd day. Okay.
Because it is not possible to bring the machine over here. We have arranged a visit also for you, but for operational purpose, for demonstration, it is better to see the video which has been made in our lab. depending upon the scaffold. It generally takes 2 to 3 minutes. Same for LSV. These are the most widely used techniques these days. Everyone is working.
The shape of voltammeter and the potential range we are taking depends on the material and the application we are working on. And for cycling voltammetry, it is very important for optimizing the potential range. So what is the main potential range in which we have to analyze record the charge discharging of during supercapacitor. So these are precautions we have to take sometimes. Otherwise, if you take from 0 volt to 5 volt, then the graph is going up, and you get nothing. So cycling voltammetry is very important technique for that purpose. It tells us about the limitations of our electrode material. Sometimes when you perform cycling voltammetry, the potential range becomes from 0 to 0.5, or sometimes minus 0.2 to 0.5, or sometimes 0 to 1.4. And there we have to also take precaution for electrolyte. We have to take the stability of electrolyte. Otherwise, we are doing a cycling voltam, performing scan rate of this potential range. We have taken 1 to 2 volt, but for HER it is 1.23 to 1.23 volt for HER to occur. So water get started splitting at 1.23. So we have to take precaution during recording the voltammeter or cycling voltammeter, whether it is LSV or any voltammeter. So there are some precautions, and
We are now ending the tutorial session also. He is waiting outside for all of you. We'll be meeting tomorrow morning at 9:30 am in the Madan Mohan Malviya Teachers Training College, also known as Academic Staff College. The location will also be shared in the WhatsApp group. At 9:30, please come at 9:30. There will be attendance in each and every session. Thank you very much. Assignment questions will be given to you tomorrow. And you will be having 2 days. You have to submit on the last day in the morning. For online participants also, we are closing down the session. We'll be meeting tomorrow morning 9:30 am sharp. Thank you.